So today we will finish this Cooper instability that we started last time. Remember, the Cooper instability can be represented by a ladder diagram, and we sum up all these ladders to infinite number of bubbles inserted, and we will get the so-called this Bethe-Salpeter equation, which is the integral equations. Remember this. So this is the integral equation that we started last time. That is kind of a vortex corrections to the, say, electron-electron interactions due to electron phonon is given by the bare one plus this ladder diagram, where this shaded oval on the right-hand side of this equation is exactly the same as the shaded circle on the left-hand side, because both shaded oval circle represents the infinite number of ladders, as we discussed last time. Okay, so you simultaneously destroy two electrons carrying opposite momentum k and minus k, but q is the momentum transfer, which is almost zero. And then those two electrons interact with the attractive interactions and many times, okay, before they get scattered out. So you sum up all such contributions, and this is called the ladder diagram. And we will show today that for temperature below, say, some critical temperature and momentum transfer goes to zero limit, this diagram diverges, okay, which we call the Cooper instability. So last time we have formulated this vortex function T, which is the bare one, U as a function of k minus k prime, which is Q. But this is the so-called the bare level. But the first non-trivial corrections to the bare interaction is given by this integral. Okay, so this minus sign is here because we are dealing with the particle-particle diagram. When you perform these weak contractions, you're going to move this creation destruction operators, and so that you could have this Green's functions, right? But when you do so, there are four operators in this diagram in general. So we move these operators around because the Fermi operators satisfy this anti-commutation rule. So by anti-commutation rules, you may end up getting an extra minus sign, which is the case here. Okay, so this is the integral equation that we should solve. This is the end of the last lecture. Okay, so we will start from here today, and we will try to solve these integral equations with the proper approximations. So in general, this U takes very complicated form as function of k minus k1, or as function of momentum transfer q, but we could simplify this and we still get reasonable solutions compared to the experiments. So this is the achievement made by BCS, Bardeen, Schrieffer, and Cooper, and we will, this is another way to formulate the BCS theory, but we could solve this by proper approximations. This integral equation is solvable if this function, this, say, U interaction strength U as function of two momentum k and k prime, or k minus p, is actually separable. So we will try to make the following assumptions and approximations. Suppose this complicated interaction strength is a function of two momentum, but even more is a function of k minus p, could be separable or could be divided into the product of the two functions, and each of the function depends only on one momentum only, which is omega k start and omega p. Suppose this is the case, and this omega star here is function of a k, and omega p here is function of p. Okay, suppose this complicated interaction strength is separable, meaning you could separate this U as function of Q in terms of these two independent functions of K and P. And furthermore, so here this lambda 0 is actually coupling constant, which is negative. Remember that. This electron phonon mediated electron-electron attraction is actually overcompensating the repulsive Coulomb interactions. So the net electron-electron interactions is attractive, and which is represented by this negative value lambda 0. And here comes the BCS assumption. So the BCS further assumed a very simple naive situation where this U as function of a K minus P, or omega K star times omega P, is nothing but a constant within, say, a range in this omega space. Because we know that this electron-electron interactions are mediated by electron phonon, and the Debye frequency omega d is served as a cutoff, natural cutoff. So the BCS further assume that this attractive interaction is given by a minus times a coupling constant g. So remember, this lambda 0 is nothing but minus g, and times the theta function, which means that this is nothing but a constant in energy spectrum or in momentum variables. So you get a very flat or just negative constant in between this plus minus omega d. So yeah, this should be a magnitude. Okay. So which means that within this plus minus Debye frequency, within that range, the U of K is nothing but a constant. It's just a minus G. Okay, so this is really naive and very crude approximation, but it turns out that this approximation works extremely well, at least for ordinary metals. So it means that you don't need a complicated interaction U to actually solve this equation. So you could assume that this U just a constant. But of course, we know that this is not very accurate, and you may have some kind of dispersion of this U in both K and omega space. But nevertheless, this kind of deviations from this potential well-like behavior is not so important. Okay, so you'll see that this prediction made by the BCS with the help of this assumption works very, very well. So let's just take this very naive assumption and consider this U as function of K minus K1, just a minus G as constant, and we simply just can put this out of this integral and see what happens. So when we do so, and we will have the following form. So let's just leading three terms and of this vertex function. So following this BCS assumption, remember the lambda 0 is negative coupling constant minus G. So the first term is negative constant, and the second term is actually minus a positive value, and the third term is actually minus again. So you could sum up all these terms as the Dyson type equation, geometric series, and what you get is this one. Good. So you simply just do this iterations right here by plugging this t by this kind of zeroth order and the first order correction, and up to zeroth order, this is just lambda 0. At first order, you get lambda 0 minus this term, and you simply get this second term, and so on and so forth. So you could iteratively plug in this t right here on the right-hand side by using this t of the previous step, okay? And then this is a geometric series, and this is the summation, the final result when you sum up all this geometric series, which means that we need to calculate this denominator right here. And later we will see that this denominator may vanish or will vanish. T goes to 0 limit and Q goes to 0 limit. So, which means that the denominator becomes 0 in these limits, and as a result, this T or vortex function diverges in that limit. Okay, so this is called Cooper instability, and we will study how this denominator vanishes in such limits. Okay, so let's take a short break. So let's continue evaluating this Cooper instability, and this is the integral in the denominator. Okay, so the stuff in the brackets appearing in the denominator right here with the dot 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 represents this integral. And remember, the lambda 0 is minus g, and as a result, if this integral becomes positive, and this everything in the denominator 1 plus lambda 0 times this bracket may vanish, okay, because this can be, and we'll show that in just a moment, this is exactly a positive value, okay, in this small momentum transfer limit and also low temperature limit, and lambda 0 is attractive coupling constant minus g, and this is 1 minus g times this positive value, so as a result, this denominator may become 0. Okay, so this is precisely what happens when the Cooper instability occurs. So here, this Q is a momentum transfer, as I mentioned, defined earlier. But this can be, this is just a 4 vector, which means that it carries the energy component or frequency component Q0, and a 3 vector Q, which is a momentum transfer in Q space, and Q0 is the Matsubarra frequency, but here the Matsubarra frequency of Q0 here is actually a bosonic type. Remember, you get 2 electrons, they are scattered by the effective electron-electron interactions, and this Q, the 4 vector Q, actually represents the momentum and frequency transfer, and you know very well that this electrons carry Matsubarra frequency, which is the odd Matsubarra frequency, and so this electron come in and go out. The difference between this Matsubarra frequency of electrons must be even a Matsubarra frequency, because this odd plus or minus odd, another odd, must be even, right? Okay, so this is, say, omega 1 and omega 2. Both omega 1 and omega 2 represents odd Matsubarra frequency for fermions, and any combinations of this omega 1 and omega 2 will lead to even Matsubarra frequencies, right? 2 odd numbers, when you add them up, becomes an even number. 2 odd numbers, when you subtract from one another, you get again even number. So odd plus odd is even, odd minus odd is also even. Okay, so this Q0 carries even Matsubarra frequency, so this is a very important point right here. And we need to we need to remember that Q0 is the even Matsubarra frequency. Okay, and we could rewrite this kind of product of the 2 Green's functions in terms of this kind of a subtractions of simple bare Green's functions carrying simple pole, and so this is a simple single pole Green's function. This is another one. You subtract this from that, and you multiply by this factor. You go back to this same product. Okay, so in other words, when we perform this, say, Matsubarra sum of P0 right here, we should separate this kind of product of 2 Green's function in terms of the difference between these 2 single particle Green's function. Okay, and as a result, we could apply this residue theorem, and this kind of for a simple pole function like this, you simply just subtract this residue of first term from the second term, you get the final result. Okay, so P0 here represents this fermionic mass bar frequency for electrons. So you simply just follow the rules that we already mentioned many lectures away, that you sum of this mass bar frequency of the simple pole function, you should get this Fermi function right here, and the residue of this pole. And so let me just double check this. IP0 right here. So with this simple pole, you get position epsilon p plus q minus iq0. For this one, you got a pole at minus epsilon p. Okay, so you plug in this pole positions right here, right? But there's no p0 here, right? So for p0, this is just a constant. So you get the common denominator right here, and then two Fermi functions, and you subtract one Fermi function from another. Okay, but remember, for example, this first Fermi function is obtained when you plug in this pole positions. So you sum over this mass bar frequency for p0. So this happens when z is actually epsilon p plus q minus iq0, right? Okay, so this happens when z, which is the generalized complex variable for IP0, hit the pole, and this pole occurs epsilon p plus q minus iq0, and this is precisely this position here. This should be f0 of z, and z hits the pole, which is this one. And likewise, the second simple pole is picked up when, say, z becomes minus epsilon p, okay, which is precisely this guy. Great. So let's just further analyze this result. And first of all, this f0 at epsilon p plus q shifted by minus iq0. This is the same as f0 epsilon p plus q. f0 refers to the Fermi function. As I mentioned, this q0 represents the even mass bar frequency, so let's just plug in this the Fermi function right here. Okay, so I simply just shift this chemical potential Fermi energy away. So this is the Fermi function. Okay, so what does that mean? If you have this imaginary component of this, in this exponent right here, unfortunately this doesn't do anything, because remember, this q0 represents even mass bar frequency, right? Okay, so if you plug in this to this the extra exponential factor, which is e to the beta minus I q0, and beta q0 is what? This is e to the minus 2 pi n I, right? Okay, so q0 is 2n pi over beta, so beta is cancelled, you get e to the minus 2 pi I times the integer number, which is precisely 1. Okay, so even if you have this very strange imaginary part in this Fermi function, but for the even mass bar frequency, it doesn't do any harm. So you could erase this minus iq0, because this eventually gives you just 1. Okay, and then you can actually continue. So now you get this f0 epsilon p plus q minus f0 minus epsilon p. So as I mentioned, this Cooper instability occurs when this momentum transfer is really tiny, or this little q is almost 0. So let's just look at this limit. So in this q goes 0 limit, this difference between these two Fermi functions becomes f0 epsilon p minus f0 minus f epsilon p, which is given by hyperbolic tangent epsilon divided by 2t. All right? Okay. So let me just write it here. Q goes 0 limit. So let's just collect all the terms in the denominator. Sorry about this. This is plus, but there's a, I didn't see there's an extra minus sign right there. Okay. So still this is plus sign. but then if you look at this extra minus sign, overall minus sign there, so there should be a minus sign right here. And yeah, still this vertex function carries plus sign in this denominator, but when you carry out this, say, Matsubar sum, and you get extra minus sign. So that's where you have this extra minus sign from Matsubara. This is P0. Okay, so then we look at this denominator, which is, say, 1 plus g. Remember, lambda 0 is just negative constant. Okay, but you'll see that this IQ 0 minus 2 epsilon p right here in the denominator. And as I mentioned, this Cooper instability occurs when momentum transfer q. But this q0 is an even Matsubara frequency and should also go 0. Okay, because this represents this external frequency that you inject in your system. Okay, so but this can be done because this q0 carried even Matsubara's frequency, and this little n here could actually go to 0. Okay, so when this little n goes 0, this q0 becomes 0, and in that limit, you get the divergent behavior. So let me just use the extra 1 minute. Okay, so this is actually, leads to divergence of this vortex function. Okay, when q0 goes to 0 limit. So remember, there is another minus sign right here, which leads to the following denominator. And you could convert this momentum integral into energy integrations and multiply by density of states at the Fermi level, and you get this denominator. So you multiply this to minus sign, you get the plus sign, but remember this is lambda 0 times density of states at Fermi level and energy integration between, say, minus and plus divide energy. And the integrand inside the integral is hyperbolic tangent of epsilon divided by 2 kBt divided by 2 epsilon. And next time we will finish this, and this can become 0 when temperature is low enough. Okay, because this integral is positive and lambda 0 is negative. And so as you lower temperature up to some point, this could be exactly canceled by this number 1 right there. So this can be 0 as long as T is low enough. Okay, so time is up. Let me stop here, and we will continue finishing this Cooper instability tomorrow.